Howdy everyone, and welcome to another video lecture in trigonometry. This time we are doing another full standalone lecture, and we're focusing on right triangle trigonometry with some real-life applications thanks to examples. Students at the University of South Florida, please remember this is section 6.1 content from our book. And for those of you who are not students at USF, that book is Pre-Calculus, a Unit Circle Approach, 4th edition. Now, to get us started, let me remind you, or let me inform you if you haven't heard this before, that when I teach trigonometry, I begin with the unit circle approach. I use the unit circle to define sine, cosine, etc., and then I calculate using information from the unit circle. And there's a lot of really good reasons to do this. The big one being that circles are geometrically so nice that a lot of the properties of circles can then be inherited by these trig functions, which is very handy. Calculating the values of trig functions of angles then becomes a matter of figuring out which properties of the circle to use. For example, reference angles, which work because of the symmetries of the unit circle. However, if you have learned trigonometry prior to this course, prior to this video, odds are very good that you learned through right triangles. I don't want to admit to how many years ago this was, but I also started learning trigonometry through the use of right triangles, and this is a very long-standing tradition. People have learned trigonometry through right triangles for probably millennia at this point, maybe more than just millennia, maybe tens of millennia. Probably the big reason why is because right triangles are easy to draw, and they obviously pop up in many physical situations. In fact, take this as a challenge. Go out today, tomorrow, the next time you think about it, and look at the objects around you and see if you can relate them to one another or map out distances using a sketch of a right triangle that joins the objects or the distances together. If you can do that, if you can find a place where you can draw a right triangle, then knowing something about right triangle trigonometry definitions will let you understand more about those objects, how far they are apart, where they are relative to you, how tall they are, all sorts of information which is very useful and which is needed in many disciplines. Physics and engineering need a lot of this sort of right triangle approach. Astronomy needs it. Navigation needs trigonometry all the time, because if you want to circumnavigate the globe, you better know how to find your bearing through the use of trigonometry. If you want to know where you are relative to some sort of obstacle, trigonometry is your friend. Actually, trigonometry pops up also in one of my favorite hobbies, which is historical European martial arts. Specifically, trigonometry plays a big role in fencing, which I think is absolutely amazing. To show you what I mean, I have an example here, which is taken from the website wichtenauer.com. I will include details in the video description. And this picture comes from an old 15th century fight manual called Il Fior di Battaglia. What's happening in this picture is we're seeing a freeze frame of a technique being played out. The person with the garter on their leg is what's called the master of the play, the master of the technique, who is doing the technique properly on this other person who I'm going to call the adversary. Basically, here's the situation. They were fighting one another. At some point during that fight, right before this picture, they had probably crossed swords somewhere between the two of them, and then the adversary, thinking he saw an opening, went after the master's leg. The master, in response, almost certainly drew back his right leg and then attacked at the head, neck, or shoulder of the adversary. The trigonometry in this picture is not immediate to see. It's not necessarily obvious. However, it explains what we're seeing in the difference in distance. If you notice, the master is easily able to land a strike on his adversary, but the adversary isn't able to touch the master at all, even though all the master probably did to avoid the strike is draw back his leg. The reason for that is to do with right triangles. If I start at the shoulder of the adversary and then draw a line out straight and horizontal, which represents the longest possible distance that the adversary could strike at the master. And then, starting at the same vertex point or corner of a triangle, I draw out a straight line that more or less duplicates the angle of the attack at the master's leg. I can then create a right triangle by joining these two sides, roughly speaking. And you'll notice that what's happening is the master is attacking more or less along this straight line between the two of them at shoulder level, but the adversary is attacking along the hypotenuse of a right triangle. And what do we know about the hypotenuse of the right triangle? Well, thanks to the Pythagorean theorem, we actually know that it is the longest side in this right triangle. That's the reason why the master can reach the adversary, but the adversary can't reach the master, because the adversary is taking this longer path to the master, whereas the master is taking a shorter path. Applications are all over the place, and they are very fascinating, and to understand how to use them to glean more information about our surroundings, we're going to need the following definitions. Scrolling down, we have the definitions that we need, and we have a diagram to go with it. You'll notice that I'm using the abbreviations ADJ, OP, and HYP, or HIP, to mean adjacent side, opposite side, and hypotenuse. Which one is adjacent, opposite, or hypotenuse is determined by the relationship with the angle. So if we look at this picture here, I've drawn theta, our angle at the bottom left-hand corner, like we would expect. We have the right angle here at the bottom right-hand corner. And so the side right next to the angle theta is the adjacent. That would be the side, not the hypotenuse. The hypotenuse is, of course, the hypotenuse. The side opposite theta is the opposite side. At first glance, these may look a little bit different from the definitions that we've given before. However, if you examine this diagram just a little bit more, you'll see that actually the definitions I've given for cosine, sine, tangent, etc. match exactly. Now, if we were going to be doing the unit circle definition, the way we would do this is we would draw out the ray that defines our angle theta and find the terminal point on the unit circle, which I've indicated here in red. We would figure out horizontally and vertically how far we've displaced from the center of our circle. And then, if we were in the unit circle, we would say we only really need the horizontal distance and the vertical distance. But in general, so it's okay to write it here, what we would do is take the vertical and horizontal distances and divide them by the radius of the circle that we're using. In the unit circle case, it just happens to be 1. This means that we wind up with an x-coordinate of x divided by 1, which would be cosine, and a y-coordinate of y divided by 1, which would be sine. This triangle, though, and the coordinate that goes along with it, or the coordinates, I should say, happen to be related to this bigger triangle, which is a similar triangle. And what do we know about similar triangles? Well, one of the things that we know about similar triangles is if I take side lengths, let's work with cosine as a good example here. If I take the side lengths that go along with the adjacent side of my small triangle here, that would be the horizontal distance in the unit circle, divided by the distance along the hypotenuse made by the radius of our circle, and I compare it to the horizontal distance in my larger triangle compared to the hypotenuse of my large triangle, like I'm doing for cosine here, these two amounts must be equal to one another. It's one of the properties of similar triangles. So in fact, the definitions that we've given here for cosine, sine, etc. are exactly the same as the definitions that we've been given before. There's just one technical detail that we should add here. In the unit circle definition, we didn't have to restrict theta at all. All we said was, once we have found the angle theta and we found the terminal point for theta, the first coordinate, the x-coordinate, is cosine, and the second, the y-coordinate, is sine. However, in order for us to draw a right triangle, we have to put a restriction on theta. And so for all the definitions above to work, we are assuming that theta is between 0 and 90 degrees strictly. I could also write that using radians. However, degrees are a little bit easier to use in applications, and so throughout this whole section, I'm going to be assuming that we're working in degrees unless I say otherwise. While you are writing these definitions down and this restriction that's necessary down, let me go ahead and also introduce something else, a sort of mnemonic. Probably you've heard it before. If you haven't, this is a good way of helping you remember these definitions that I've put up here. It goes something like this. So, ka, toa. Now, what does SOHCAHTOA mean? Well, if we look at sine, for example, sine is opposite over hypotenuse. So when I write so, what I am really saying is sine is opposite over hypotenuse. When I say ka, C-A-H, what I mean is cosine is adjacent over hypotenuse. Cosine adjacent hypotenuse. And tangent then becomes opposite over adjacent. These simple mnemonics are a good way of helping you remember the definitions while you're still getting used to them. And with all this information in front of you, I think this is a good time to go ahead and test out these definitions with some example calculations. So we have an example. Calculate all 6 trigonometric functions for theta, where theta is the angle that we see in this diagram here. Now, before we begin, let's go ahead and label these sides. It's very easy for folks who are getting used to doing these sorts of calculations to get misled, so let's remember. When I talk about opposite, adjacent, and hypotenuse, here's what I'm looking for. The side adjacent to theta is the side that lies between theta and the right angle. So that would be this side, I'll go ahead and label it for you, right here. This side is the adjacent side. The side opposite theta is the other leg of the triangle, not the hypotenuse, other than the adjacent. So that would be this side here. And of course, the hypotenuse is pretty easy to find. It's the one opposite the right angle. Now that we have these definitions, it's easy enough to do the calculations. Since the mnemonic starts with sine, let's go ahead and calculate sine first. So if I want to take sine of theta, remember that sine of theta should be the opposite divided by the hypotenuse. So if we consult our figure here, we quickly see that that's going to be found by taking 7 and dividing it by 7, the square root of 2. This can be simplified. Obviously, we have a couple of 7s hanging around, so I can cross out the common factor of 7. This will lead us to 1 over the square root of 2, and hopefully everybody will be familiar with how this rationalizes. It should be root 2 over 2. If we move on to cosine, well, cosine of theta should be the adjacent side divided by the hypotenuse. And actually, that's going to be exactly the same calculation. We'll have 7 divided by 7 root 2, and we can just continue this workout and say it will be root 2 divided by 2. Now, we are going to calculate the rest of the trig functions, but from this point forward, I'm just going to show them completed one after the other after the other. So do yourself a favor. Pause the video before I show the next calculation. Do it yourself and compare your answer to my answer. Use it to try and help yourself see if you've got it down right, although I'm pretty confident you have. All right, tangent next. From the definition, I clearly get 1. Now let's do cosecant, the reciprocal of sine, which gives you another way of calculating. That will be, whoops, in the wrong spot. After the smoke of quote-unquote battle, we should get square root of 2 as the simplification. Okay, now secant. Once again, just like with sine and cosine, cosecant and secant should be equal, and that leaves only cotangent. And predictably, since tangent was equal to 1, cotangent, its reciprocal, is also equal to 1. Okay, let's do a slightly more challenging problem. Scrolling down, we have another calculate all 6 trig functions sort of problem. The difference is that this time we don't have all of the information for this triangle. However, that's not much of an impediment. We already happen to know how to work with triangles. We talked about it a little while ago. We happen to know that in triangles, with our right triangles, we can always call upon the Pythagorean theorem. In this case, since I don't know the side opposite theta, I'll go ahead and give that away. This is clearly the side opposite theta. All we need to do is use the relationship of the Pythagorean theorem to figure out what the missing side is. So let's do that really quickly. So let's see. According to the Pythagorean theorem, what should happen is if I take these two sides, so let's say 15 squared, and then add to it the unknown side, which I think I'll call x for right now, squared, the result should be the same thing as 17 squared. Clearly, I can rewrite that by subtracting 15 squared from both sides. So I'll have x squared is equal to 17 squared, and I'll subtract 15 squared to make this all balanced. Now, I don't want x squared. I want to know what x is, so I'm going to go ahead and take a square root of both sides. Students will know by now that I like to double check when I take the square root that what I'm doing makes sense. But remember, since we're dealing with a right triangle and x is the length of this side of the right triangle, the positive number, which this square root is guaranteed to give us, positive or 0, but positive in this case, is okay. It makes sense for our context. So I don't need to worry about what symbol, plus or minus, to put out front. So it looks as if what I'm going to find is that x is equal to the square root of the difference of 17 squared and 15 squared. Go ahead and try that in your calculator and see what you get. According to my calculations, that appears to give me 8. So, the missing side is length 8. Now I can go ahead and label sides once again like we did last time, but this time I'm just going to do it fast. Again, pause and test your knowledge here. Make sure you're getting the same labeling I do. And once I have all 3 sides, I have the position of theta, and I also know which sides are which. For my labeling purposes, I can calculate the 6 trig functions. I'm going to do them all in one fell swoop. So you guys go ahead and work them out in one fell swoop as well. All we have to do is use exactly the fractions that we were working with before. If you need to go back, go look at them. All right, here it goes. And there they are. Sine all the way through cotangent. Nothing too difficult. Again, all we're using are the definition fractions that we gave up above and on the previous page. So let's go ahead and introduce another problem, again a little bit more challenging. We'll leave out a little bit more information again. Making our way down page. Here we go. We're going to be given some data, the data here, and we're going to use that to obtain a couple of trig function values. Specifically, knowing that cotangent of an angle theta gives us 6 over 11, we're going to find out what sine of theta and cosine of theta are. Well, the first place that I like to start in a situation like this is by drawing a picture. So I'm going to come over here and just draw a mock-up picture. It's not going to be perfectly to scale. All it's going to do is give me a starting place for visualizing my information. Since I'm the one drawing this, I can decide where theta gets to be placed. So I'm going to place theta here. And then I have the various sides of my triangle, and I need to fill them in. How am I going to do that? Well, if I go back to my definition from up above and also from the previous page, whenever I talk about cotangent, I am talking about taking the side adjacent to my angle and dividing it by the side opposite my angle. So, looking at the fraction that I have here, it looks like there is an easy way to use this information to start filling in the blanks. The side adjacent to my angle theta, which in this picture would be right here, would be 6. Let me go ahead and write that down real quick. This side length here would be 6. And then this side here, the one opposite theta, that would be length 11. Now, there may be some of you who are a little bit more technically minded. If you are, good, that's not a bad thing, who may be saying, how do we know for sure these are the right lengths to put in here? Well, we actually could draw other triangles. We could draw bigger ones or smaller ones. So, for example, if I just want to sketch one really quickly, I could sketch, let's say, a smaller one just for space considerations. It will be another right triangle. The bottom corner will be theta once again, and this time the lengths of the sides will be different. I don't know what the lengths of the sides would be in this case. That's not really the important thing. The important thing is to remember, since they are both right triangles, meaning this bottom right-hand corner is 90 degrees, since they both have the angle theta at the bottom left-hand corner, they also both have the same upper corner. That means that these two triangles, rough though they are in my picture, are similar triangles. And once again, if I were to start calculating cotangent using that adjacent over opposite approach, for me, that would be x over y. But then if I calculate cotangent for this red triangle, 6 over 11, because they are similar triangles, once again, these values must be exactly the same. And what that means for us is, I don't need to draw the triangle one specific way. If you want to draw the triangle exactly the way I did, that is probably the easiest way. If you find another triangle that will give you exactly the same value of cotangent, then by all means, go for it. If you find another triangle, it will be a similar triangle, and because it is a similar triangle, your answers and mine will match exactly. Okay, getting rid of those, let me go ahead and simply call the missing side, which is the hypotenuse h. Oops. Let's call that h. And let's go ahead and solve for h. By now you guys know, in fact you can see a bit of our previous work, we're going to be using the Pythagorean theorem. So go ahead and try to do the Pythagorean theorem yourself. I'm going to do it as well. Pause the video, do the calculations, compare your work to mine. Here we go. All right, adding the squares of 11 and 6 together and then taking the square root, it appears that I find that the missing side, h, is square root of 157. You can check it. It's kind of an ugly answer. Now that we have this information, we can calculate sine and cosine. So I'm going to do that one at a time off to the side. Once again, go ahead and check your calculations against mine. We'll do sine first. Since I know that 11 is the side opposite, and h is the value we just calculated, and that is the hypotenuse, we simply get 11 over root 157, or 11 the square root of 157 divided by 157. Now we can do cosine. We almost ran out of room here. Once again, test your knowledge. Here we go. Since the side adjacent to theta has length 6, we find out that cosine of theta should be 6 divided by root 157, and we can simplify that, or rather rationalize that, as 6 square root of 157 divided by 157. Okay, now that we've done a couple of simple calculations using these definitions, let's use these definitions a slightly different way. It's kind of neat. because before, one of the things that I said, and I mean it and meant it, was that it's frequently the case that the unit circle definition allows us to get more insight into how these trig functions work. But there are some cases where the right triangle approach gives us some good information. So, switching to this picture here on the next page, I've set up a right triangle whose bottom left-hand corner has an angle of theta, and whose upper right-hand corner, or maybe just upper corner, is phi. You'll notice I've also used a single arc line for theta and double for phi, and that's common. It's just supposed to denote the fact that they are different angles. Well, what does this picture tell us? Well, one thing we know is what the relationship is between theta and phi. See, we already know something about all right triangles, really about all triangles, and that is if I take all three angles and I add them together like so, then the result must be 180 degrees. This is a very well-known property. Now, what I could do is I could rewrite this. I could then take this 90 and subtract it from both sides and rewrite this statement equivalently to say, if I take the angles theta and phi and I add them together, the result must be 180 minus 90, or in other words, 90 degrees. And actually, we can even go a step further. I can rewrite this again equivalently by subtracting theta from both sides. And what I'll find out is the upper angle, phi, is the same thing as 90 degrees minus theta. Now, why is that important? Well, because of how this works with calculations and something that we called before the co-function identities. Let me go ahead and refresh your memory a little bit. Let's say, for example, that I was trying to calculate cosine of, let's say, theta. Now, based on what we know about right triangle trigonometry, cosine of theta means I take the adjacent side with length x and divide it by the hypotenuse with length r, and this would be our answer. Notice, however, that if I were to come from the other corner, let's say from up here, x is the side opposite. R is still the hypotenuse. So actually, that fraction x divided by r, if we come from the upper corner, would be the same thing as what we get from sine. Remember, sine is opposite over hypotenuse. So when I take cosine of theta or sine of phi, I get exactly the same result. Well, based on my calculation up above, another way of saying exactly what we wrote a few seconds ago is cosine of theta and sine of 90 degrees minus theta are exactly one and the same, and this is one of the cofunction identities. If we were to start with sine, we could do a similar calculation. Based on what we know, sine of theta should be the side opposite divided by the hypotenuse, so y divided by r. How about from phi? Well, from the position of phi, if I want to get y over r, I should be doing cosine, the adjacent side to my angle divided by the hypotenuse. Since phi is exactly the same thing as 90 degrees minus theta, if I wanted to do cosine of phi, y over r, I could also just as easily do cosine of 90 minus theta. And so we get the next of the cofunction identities. Sine of theta is equal to cosine of 90 degrees minus theta. There are others of those as well. I'll go ahead and put them on the screen. There are a total of 6 cofunction relationships. I've written them all here for you so we can use them all, and in fact, we're going to use them in the next example. Let's try to keep them on the page. Okay, example. Given that cosine of 37 degrees is approximately 0.7986, find sine of 53 degrees. If we hadn't put all these identities up here, you might think to yourself that this is actually a very challenging problem, but it's not, because all we need to do is check and see if these guys, 37 degrees and 53 degrees, are related by being opposite corners or other corners of a right triangle. Or, to put it a slightly different way, the way I'd really like to go, what I'd like to do is check and see, is 37 degrees equal to 90 degrees minus 53? Well, if you plug this into your calculator very quickly, you will find out that yes, indeed, if I take 90 degrees and I subtract 53 degrees, I get 37 degrees. Also, we can go the other way around. If I have 53 degrees is what happens when I take 90 and I subtract 37. Because I have all of these co-function relationships, these co-function identities off to the side, I can now put them to good use in my calculation. I can write sine of 53 degrees, which is the desired value I want to get, and that's going to be the same thing as cosine of 90 minus this angle 53, which turns out is cosine of 37 degrees. And we've already been told what cosine of 37 degrees is approximately. It is 0.7986. And there you go. Calculation done. Let's do another. Let's say that I'm told the cosecant of 78 degrees is approximately 1.0223. Find secant of 12 degrees. Now that you know basically what to look for, I'm going to let you do this yourself. I'm going to let you pause the video, do the calculations, and then check them next to mine. So let's start with the first step. Pause, do that, and then come back. All right, my first step is to work with these angles and to see if they're related if they're related through the equations that we should be working with. That is, I need to see if, when I start with 78 degrees, it is the same thing as 90 degrees minus 12 degrees, which it is. And I also need to check to see if 12 degrees is what I get when I take a 90 degrees and subtract 78 degrees. And again, it is. Truly, we only need one of those. I'm sure you guys realize that by now. If you look through our work and through the relationships up above, it turns out that this one is the one we really want, but it doesn't hurt to do both. Also, frankly, this video is being recorded a week after Hurricane Milton, and I'm just a little bit tired, so I'm going to go ahead and go with brain lapse due to hurricane. Okay, now that we know both of these relationships, and in particular, we know the important one, let's go ahead and do the calculation. Again, pause, check it against what I am about to do. If I can keep my brain together. Here it goes. Using one of our co-function identities, I realize that secant of 12 degrees is the same thing as cosecant of 90 minus 12 degrees. When I do that inner calculation, I get cosecant of 78, and cosecant of 78 is our known value, so I have our approximate answer. Okay, so much for the basic stuff. We understand how to calculate the various trig functions given triangles. We also have figured out how to use co-function identities from the right triangles and how to use them to calculate the values of trig functions if we have a little bit of information. So now it's time for a new term, something that's going to be important throughout the rest of this chapter, and it's going to come from a definition. So let me go ahead and start that right here. And through the power of video editing, let me fill in this definition. Okay, if we know some information about a triangle, Then we are said to have solved that triangle once we have found or calculated all of the side lengths of the triangle and all the angle measurements. Now, in this section in particular, with right triangles, this is made a little bit easier. For one thing, we know one of the angles is always going to be 90 degrees. For another thing, we know that the three sides are related by the Pythagorean theorem. Finally, we also know the sine and cosine, etc. relationships on the triangle. So once we have that information, we can use a little bit of given info to find all of the rest of the info for that triangle. Now, I am also going to introduce something that I have not done before, so let me draw a right triangle quickly. Many times when we are working with triangles, we use the generic labels A, B, and C in uppercase and lowercase for the various pieces, parts of our triangle. Typically, the way it goes is the uppercase letters represent the angles, and the lowercase represents the side lengths. There are also a couple of conventions that we go with. The first is that C is the right angle, and that little c, the side opposite, is the hypotenuse length. After that, it doesn't matter which of these two other corners is A and which one is B. All that matters is that we're consistent and that we label things exactly the way that I did with big C and little c. If I make this left-hand corner big A, then this right-hand side, the side opposite, needs to be little a. On the other hand, if this corner on the right-hand side is big A, then this side on the left, the side opposite, needs to be little a. Similarly for B, wherever big B gets placed, little b is the side opposite. Let's go ahead and try solving a right triangle. Moving to the next page, we have our example. Solve the right triangle given that big B is 28 degrees and little c is 10.5 units. It isn't specific about units, but remember, it is a measurement of length, so there should be units. Whenever I'm faced with a problem like this, the first thing I do is I draw a picture, and I usually draw a picture with the bottom right-hand corner being my right angle, and my given angle being the bottom left-hand corner right here. We already know that that makes this corner here the right angle C. This side here is little c. This side here is little b. A must be up here and little a must be down here. And we also have the information, so I'm going to go ahead and fill that in quickly. And now we should try to figure out what to solve for next. Now, I've said this many times in class, and I'll say it here as well. As a mathematician, I always strive for intelligent laziness. I should try to find out information as quickly and as easily as I possibly can, and there is an easy and quick calculation I can do. I already know that B is 28 degrees. I already know that C is 90 degrees, so I already know that whatever A is, I can find it by taking 90 degrees and subtracting away 28. So let me go ahead and do that calculation first. A must be equal to 90 degrees minus B, or in other words, 90 degrees minus 28 degrees. In this particular case, that yields 62 degrees. You can choose to write it up here in your triangle if you like. It's not absolutely necessary. Okay, I now know what big B, big A, and big C are. I know little c, but I don't know little a or little b, so now I'm going to have to do a little bit more work. Since I started out with big B, I may as well go ahead and figure out what little b is, so I'm trying to think. What information relates this side with length little b to the other information I've got? Well, I started with big B the angle opposite little b, and the hypotenuse length little c. So what if I use the relationship of sine? Remember, sine is opposite over hypotenuse. So if I want to solve for little b using the information I was given, then one of the things that I should note is that if I take sine of big B, sine of 28 degrees, then I should be calculating that by taking the side opposite, the unknown, and dividing it by the hypotenuse, which is 10.5. I could rewrite this by multiplying both the left and the right-hand sides by 10.5. So if I do that, I will have little b is equal to 10.5 times the sine of 28 degrees. And technically, this is the correct answer. We are going to have to approximate just a little bit. I'm probably going to approximate all of my final answers to 2 decimal places. But this is the correct, fully accurate answer. Now let's go ahead and get the approximate answer by feeding things into the calculator. Doing that, what I find is that little b is equal to approximately 4.93 if I round to 2 decimal places. I'm not going to be using the 4.93 in the next step of my calculations, just to be clear. That's just my final approximation of what little b will be. If I had to enter this into homework software, let's say, or put it on an exam, and I was told round to 2 decimal places, when I put down my answer in the little b box, I would put 4.93. Calculation-wise, though, I need to use the accurate result that we just got. Well, at this point, we have everything except little a, so we may as well go ahead and get to it. I know that little a, little b, and little c are related by the Pythagorean theorem, so I may as well go ahead and write. If I have little a squared plus, and since little b is a bit ugly, I'm going to write little b squared, then the sum of their squares should be equal to little c squared. Little c isn't so bad, so I'll go ahead and just put 10.5 squared. Kind of like we did earlier, I can rewrite this by simply subtracting b squared from both sides, which gives me the equation little a squared is equal to 10.5 squared minus little b squared. And taking a square root of both sides, and remembering, once again, if I take a square root of both sides, I'm going to wind up with a positive on the right-hand side, but luckily, a positive is what we should be getting with side lengths. Now I can go ahead and feed this into my calculator. So if I do, this exact answer for little a is going to give me the approximate answer 9.27 units. Okay, I might as well go back and double check everything. I have the angles B, C, and A. I have the sides little a, little b, and little c. So yes, I have everything. That means I have solved this right triangle. Let's do another example. I have another one of those right here. We're going to solve a right triangle given that little a is 4.3 and little b is 8.1. Based upon the previous example, the very first thing we should do is draw a right triangle. So go ahead and do that however you're most comfortable. Remember though, I'm going to be drawing one kind of like the one I did here. I'll hold off on labeling until I have it in front of us. Now, this time I wasn't given any angles, except for the obvious right triangle angle down here at the bottom right-hand corner. So I'm just going to go ahead and put little a here and little b here. I already know that this angle, the right angle, is big C, which makes this one little c. And since I want the capital letters to be opposite their lowercase counterparts, that makes this angle up here big A, and this one down here big B. So actually this is very much like what we drew last time. I also already know some of the information, so let's input that. And now, once again, we're looking for the easy pickings, the things we can do without too much expenditure of effort. Since I was only given side lengths, it sounds to me like we may as well use the Pythagorean theorem to get little c. So let's go ahead and do that up here. If I want to find little c, I know that little c squared is equal to little a, 4.3, squared, plus little b, 8.1, squared. I also know then that if I take a square root of both sides, in this particular case, I shouldn't have any issues, and the square root of 4.3 squared plus 8.1 squared should be the exact value of little c. Clearly, this is going to give us a kind of ugly calculation, so let's also get the approximate answer to 2 decimal places, just so we have that for our final answer. Based on my calculator, what I'm seeing is that we should get approximately 9.17. And that checks out because it is a little bit bigger than the other two sides, like we'd expect. Okay, now we need to get one of the angles, B or A, and I feel really awful making A stand at the top of this triangle all this time, so I'm going to go ahead and get A next. Now you might be thinking to yourself that kind of like last time, what I could do is use sine or maybe cosine. After all, if I wanted, I could say, okay, the sine of this angle here at big A would be the opposite over the hypotenuse. I already got the hypotenuse length, so that should be a doable calculation. And you're right, but normally we want to use given information as much as possible. I don't want to start dipping into this information that we inferred unless we absolutely have to. It's better to use given info. So here's a question. Is there a trig function that somehow relates little a and little b to one another? Well, actually, yes, there is. If I start at the corner A, the angle A, just to make things easier, I know that tangent of A would give me the side opposite divided by the side adjacent. Okay, so let's write that down. If I took tangent of big A, it should be equal to the side opposite, 4.3, divided by the side adjacent, 8.1. With a relationship like that, and since I know that little a is going to be guaranteed an acute angle because of the restrictions on these angles that we need to make right triangles, I'm allowed to rewrite this using inverse trigonometry. By inverse trigonometry, if I can write tangent of a is equal to this fraction, I should also be able to write a is equal to the inverse tangent of the fraction, or the arctangent, as I prefer to say. And that would be the exact answer. Obviously, that's not our final answer that we'd want to give, so we're going to get the approximation 27.96 degrees. Oh, hey, now we know what big A is, so we can find big B because they are going to be complementary angles. So, if I want to find big B, I simply note that big B is equal to 90 degrees minus the angle A, a messy angle, so I'm just writing it symbolically for now. This is the technically correct answer, but if you want the close enough for government work answer, then it would be 62.04 degrees. All right, we have all three sides, we have all three angles, therefore I declare this triangle solved. Now you may be thinking to yourself, okay, great, so we just solved a couple of triangles. What's the value of that? Well, what we've done is practiced using our knowledge of right triangles and trig to help us figure out missing side information. That means that if we could find a right triangle in the world around us with some missing information, as long as we had enough other information, we could figure out the missing information. In other words, we could use right triangles to learn stuff about the real world. In fact, I think this is a great time to segue into some real-world application style problems, word problems. So let's go ahead and do one. So we have a possible real-world situation where we have an 18-foot ladder. It's resting against the wall of a building, and we know the top of the ladder is 14 feet above the ground. We want to know how far the foot of the ladder is away from the base of the building. Now this is kind of a simple application. Also, it's not 100% necessary. After all, if we have an 18-foot ladder positioned so that the top is 14 feet above the ground, we could always get out, say, a tape measure and measure things. But we don't absolutely need to. We could use our brains and figure it out for ourselves. So let's begin by drawing a picture. I'm going to put our wall right here. I'm going to put our ladder right here like this. And what I'm going to do is I'm going to label their lengths. I know the ladder is 18 feet long. I know the top of the ladder is 14 feet above the ground. So now I want to figure out how far away the base is from the wall. As I mentioned, this is a pretty simple one. It turns out, just looking at this picture, that what we're doing is looking for this missing side here, which I'm going to call D for distance. And it looks to me like, based upon the Pythagorean theorem, if I were to take d squared and add 14 squared to it, then the result would be 18 squared. Equivalently, I could rewrite this as d squared is the same as 18 squared minus 14 squared. And this leads me to conclude that since I'm dealing with positive numbers, distances, that d must be what happens when I take the square root of 18 squared minus 14 squared. Now you'll notice in this particular problem, it's not looking for any kind of simplification, or that's not really the right word. It's not looking for me to approximate, excuse me. We're not looking to approximate in this case. So let's go ahead and get an exact answer. Based on what I'm seeing here, the exact answer should be the square root of 128. But actually, I can simplify that a little bit. I know I said accidentally we don't want to simplify, but we always want to simplify. It makes our life easier. I know that 128 is the same thing as 64 times 2. Since 64 is a perfect square, and since square roots break down or decompose nicely over multiplication, that tells me that this is the same thing as square root of 64 times square root of 2, or in other words, 8 the square root of 2. And that should be our final answer for the distance. The base of the ladder is 8 the square root of 2 feet away from the wall. Let's introduce a more interesting problem. And to do this more interesting problem, we need some new terminology. Now, I've written a lot here, and it will be worthwhile to read through it if you really want to firmly fix this information in your mind, but the picture really gives you the right idea. If I am observing from the fixed point here, the dark point, and this black dashed line represents a horizontal line, a line parallel with the ground, then if my line of sight goes above that horizontal, the angle between them that you see right here in red is called the angle of elevation. If, on the other hand, my line of sight drops below that horizontal dashed line, then the blue angle that you see beneath it, between the horizontal and my line of sight, is called the angle of depression. These are really good terms for use when we need to figure out angles relative to positions, and we're going to use them in the following problem. The angle of elevation from a rowboat moored 75 feet away from a cliff is 73.8 degrees. Find the height of the cliff to the nearest foot. So of course we're going to need a picture here. And if we're going to have a picture, we may as well go ahead and have some fun with it. So first of all, we have our boat right here. It's a rowboat. So it doesn't get to have any sails, which would be my usual way to draw a boat, but it is going to get some oars right here, just for the heck of it. And I don't know, maybe a person sitting in the boat. We know that this rowboat is moored in the water, so I'll go ahead and put some water down here, again for my own childish amusement. And it's moored away from a cliff over here. Suitably jagged looking cliff. All right, so from the rowboat up to the cliff, we have an angle of elevation. Technically speaking, the water line in this particular picture is going to act kind of like our horizontal line. So if I go up from this boat to the cliff, which I'm going to do in as straight a line as I possibly can, I get an angle of 73.8 degrees. I also know that if I measure the distance between the rowboat and the cliff, I find that it is a distance of 75 feet. I'll go ahead and put the units down here. So now the question is, what is the height of the cliff? Well, I'm going to go ahead and put the height of the cliff as h for height, and I'm going to note that even with this little wavy line here I've cutely made for water, what I've done is I've made a right triangle. So now I'm able to use what I know about right triangles and the given information to try and find h. So let's ask ourselves, in a right triangle, what would relate h, the side adjacent right here, this 75 feet, and this angle of 73.8 feet? Well, I may have actually given this away pretty quickly. Looking at this picture, I know a trig function that relates these three values to one another, and it would be tangent. If I take tangent of this angle, it's going to be calculated by the height h divided by this horizontal side of 75 feet. So I'm going to go ahead and write that here first. Tangent of 73.8 degrees is equal to h divided by 75. Since I want to solve for h, I'm going to rewrite this equivalently by multiplying both sides by 75. That will leave h all by itself, and on the other side I'll get 75 times the tangent of 73.8 degrees. It tells us to round to the nearest foot, so we're going to be rounding to the nearest whole number. And if we run that calculation through our calculators, we get, well, I get 258.1516933, etc. So the nearest foot here would be 258 feet, approximately. So apparently the height of this cliff, even though it doesn't quite match the scale of my drawing, is 258 feet and some change. I know what you're thinking at this point. Why, the possibilities are endless. We should do more. Sir, can we do more? And yes, we can. Let's have another example. So we have an example with a girl who's 5 feet tall flying a kite. How long must the string be in order for her to raise the kite 200 feet above the ground if the string makes an angle of 28 degrees with the ground? Okay, let's go ahead and draw another picture. Once again, partially to be cute, but also to have information visible in this, I'm going to draw my little girl right here. I guess I'm going to put a bow on her head. That's just the way I choose to draw her. She is going to be 5 feet tall. That is an important part of the problem. We can't forget it. Okay, we have a kite which is going to be 200 feet off the ground, which I'll go ahead and put right about over here. There's our kite with its little kite tail. We know that if we were to measure the distance from the kite all the way to the ground, we would get 200 feet. So I'll go ahead and put that here, 200 feet. We also know that the string is making a 28-degree angle with the ground. Now, that might sound a little bit weird at first, but let's remember something. When we draw out the horizontal at the little girl's head height, the horizontal is going to be parallel to the ground. So if the string makes a 28-degree angle with the ground, it's also going to make a 28-degree angle with this line right here. So if we draw our line like so, more or less, then that means that this angle right here must be 28 degrees. So the question is, how long is this string, which I'm going to label as S for string. Okay, well, looking at this picture, I'm trying to relate the side length that I was given for the height of the kite and the angle that I was given here with S. So the first thing I start thinking to myself is, okay, wait a second. So if I have a right triangle here, which I clearly do, then it must be that sine is the one I want, because sine starts at the angle, and then it takes the side opposite and divides that length by the length of the hypotenuse. Then I think about it and I think to myself, oh, wait a second. Maybe it's true that sine of theta is equal to opposite over hypotenuse. But since I want to solve for the hypotenuse, maybe that's not really the one I want. I could use it, but maybe the easier one to work with would be cosecant of theta, because cosecant of theta is hypotenuse, the amount we're going to solve for, divided by opposite. And that sounds a lot more reasonable. So my first guess here is not quite right, but it leads me to the right direction. Cosecant is going to be a little bit easier. This is also the point where our careful picture drawing, cute though it may be, kind of saves our bacon, because some of you may have noticed, while the height of the kite is 200 feet, the length of the side opposite 28 degrees is not 200 feet. Since the little girl is 5 feet tall, one of the things that we should note in the picture is, from this point to the ground is 5 feet as well, which means that from the bottom of the kite to this point here at the girl's head height must be 155 feet. In fact, let me go ahead and scoot things around so I can write that information all in one spot, because that's important to know. That's really important, and it shows the value of a good picture here. So, if I'm right, we should be writing the following. Cosecant of 28 degrees should lead us to the hypotenuse S divided by the length opposite the angle, which would be 155 feet. I can now rewrite this by multiplying both sides by 155. If I do, the length of the string will be left all by itself, and we will get 155 times cosecant of 28 degrees. Now, if you're looking at your screen right now and thinking to yourself, but Dr. Forrest, I don't know how to do that. I don't have a button for cosecant on my calculator. Don't worry. Remember, cosecant is the reciprocal of sine. It's the whole fact that we introduced, or rather reintroduced back up here. So we could just as easily write this as 155 divided by sine of 28 degrees. And this is very doable in your calculator. It looks like they don't ask for any kind of rounding in this case, so I'm going to say generically, let's round to 2 decimal places. If I put this in our calculator and round, it looks like we should be getting approximately 330.16 feet long. That should be the length of the kite string to make the situation work out. Looks like we've reached the bottom of this page, but we haven't reached the end of the problems. Let's have another exercise. Irradiating flowers. Well, now we know we're going to have a fun time. So, we have a tray of flowers, and what we're doing is we're shining a light on them, irradiating them. We're using a light that rotates from one side to the other. Now, we know the length of the tray in which these flowers are placed is 8 feet long from one side to the other. We also know that if you measure the distance from exactly where the lamp is placed to the center of the tray, we get a length of 2 feet. So the question is, what is the total angle that this lamp should rotate through in order to irradiate, or as normal people would say, to give light to all of the flowers in this tray? Well, at first glance at this picture, it almost looks like we might not have right triangle trigonometry. After all, the triangle through the entire rotation from one side to the other and then across the length of the tray is not a right triangle. However, I do see a right triangle here if I'm willing to break my picture down a little bit. What I'm noticing is that right here, if I follow this midline on the tray down and then complete the triangle on the left-hand side, I will have a right triangle, and it will look a little bit something like that. That is not the best triangle I've ever drawn, but that's okay. It's a right triangle. All we have to do now is use what we know about this triangle, the big one we were given, to label the information correctly in our small one. Now we know the length of this upright side, this vertical, it's 2 feet. We were already given that. Because we know that the lamp is positioned exactly over the midpoint of the tray, it must be that from one end, the left end, to the middle, where we've ended our right triangle, is half of 8 feet, which would make it 4 feet. But this also means that when I'm looking at my angle, the angle theta that they're indicating goes from one dashed line on the one extreme side to the other dashed line on the other extreme side, and we're only doing half of that. So the angle that we're seeing here is really theta over 2. But that's not a problem. If I can figure out what theta over 2 is from this right triangle I've drawn, then I can always take that number and double it, and that will give me the correct answer. That is going to be my logic for working with this. Okay, so we have our angle of theta over 2 here. We have the two sides, 4 feet and 2 feet, and I'm looking to relate them together. Here's what I'm thinking. Since I have an angle here, and since I have these two sides, why don't I use tangent? I'll take this length and divide it by that length, opposite divided by adjacent. This tells me that tangent of theta over 2 is equal to 4 over 2. Or, to simplify things a little bit, it's equal to 2. The unknown that I'm looking for is the theta inside of tangent. So I've got an idea. Once again, we're dealing with right triangles and acute angles. That is, angles in the first quadrant. Since that's the case, I should be able to rewrite through the power of inverse trigonometry. Instead of tangent of the half angle equals 2, I should be able to say the half angle is equal to arctangent of 2. Now I could calculate what the right-hand side is from here, but actually I don't need to. If I multiply both sides by 2, the left-hand side will become theta, the angle I actually want, while the right-hand side will become 2 times the arctangent of 2, something I can put into my calculator. I'm going to scroll back up to see what it wants exactly. So it says, what angle should the lamp rotate through? And let's go ahead and rotate let's round another R word to the nearest hundredth once again. So if I pop this into my calculator and round to the nearest hundredth, we should be getting approximately 126.87 degrees. In reality, a gardener would probably look at this calculation and say, let's just make it 127 degrees, so that way it covers the whole tray, and that's okay. But we know that a closer answer would be 126.87 degrees. All right, looking at the time of this video so far, we're getting a little bit on the long side. I always plan more exercises than I usually have time for, so let me go ahead and do 2 more. 2 which I think are going to be important, especially for my USF students. Then I'll go ahead and give the Canvas quiz question, which I promised them, and then we'll be all done. So, next question coming up fast. The problem is stated very simply. It simply says, find the radius of the 53rd parallel of latitude. Now, I believe the textbook provides an explanation of this, so let me go ahead and talk you through it pretty simply. If you can imagine, normally when we look at maps of the Earth, we look at them flat, and if we were to include the lines of latitude are lines that are parallel with the equator. They are horizontal lines in our maps that go from the bottom of the map all the way to the top of the map. When you take that map and you wrap it around into a circle, or really a globe, you no longer have lines, you have circles. So for example, you'll notice the circle that I'm tracing out right now on the Earth's surface is the equator. That is one of the lines of latitude, or really, as they're now called, the parallels of latitude, once they become circles. Each of these circles that happens to be parallel with the equator is called a parallel of latitude, and the way that we identify them is via angles. By drawing an imaginary point here at A, at the center of the Earth, drawing a line out to the equator here, and then rotating open an angle, theta, until we reach our parallel of latitude here at the point B. The angle that we go through to pass from the equator to our parallel of latitude is the angle designation for that parallel. So, for example, when I say the 53rd parallel of latitude, what I mean is the angle theta here is 53 degrees, which I'll go ahead and write down. There's one other piece of information that we need here. It's not included in the picture, but I'll go ahead and make sure that we have it here. This is pretty standard. Assume the Earth has a radius of 3,960 miles. What they're looking for us to do is to use that information about the radius of the Earth and the right triangles that you're seeing appear in this diagram in order to solve things out. But I will go ahead and be honest with you guys. I never use a diagram in 3 dimensions like what's drawn here. I find it difficult to work with. So instead, I turn this into a 2-dimensional version. So, in my 2-dimensional version, here's A at the center of the Earth. Here's the point on the equator. So I'm just going to write here EQ for equator. Then I'm going to have the 53-degree angle line, which maybe that's a little bit too big. 53 degrees ought to be something like this. 53 degrees, or in other words, theta in our picture. And then we have the point here, B, on the surface of the Earth, which also happens to be on our 53rd parallel of latitude. In our picture, this is the amount they call r, the radius of the 53rd parallel, and that's the thing we want to figure out. Okay, so there are a couple of different ways to work with this. This is the one that I think people usually see first. If you find another way, or if you'd like to talk about another way with me, either leave a comment or talk to me during class time. So, because I know that from this line between A and the equator up to this vertical line here above A, we have a right angle, it must be that the angle inside the triangle right here is complementary to 53 degrees, and that makes it 37 degrees. That's thing one. So we now have an angle inside our right triangle here, and let me go ahead and remind us of that right now. This right here is a right triangle, just like it says in our picture. We need some other piece of information. Now, some of you may be tempted to go for this other vertical side of the triangle, the non-hypotenuse leg. However, we don't really know anything about the height of the parallel of latitude. We know the angle, but not the height at which it takes place on the Earth. However, remember what I said. This line here from A to B, which forms the 53-degree angle that we see below, that line connects from the center of the Earth to B, which is not only a point on the parallel of latitude, it's a point on the surface of the Earth. A line that goes from the center of a circle, which is basically what we've described here, to the outside edge of the circle is a radial line. It represents the radius of the circle. And guess what? We are assuming the Earth has a radius of 3,960 miles. So that suggests that the length from A to B is 3,960 miles. Now that we know that, things aren't so bad. We now have an angle inside the triangle, we have a side opposite we want to find, and we have the hypotenuse, and we remember the following. If I take sine of the angle on the inside, 37 degrees, it will be the same thing as, by definition, the radius that we want to find of the parallel of latitude, the value r, divided by this length, 3,960 degrees, or 3,960 miles, my bad. We can rewrite this. We isolate r by multiplying both sides by 3,960. That leaves me with, I've got to pronounce things properly, even in a math class. R is equal to 3,960 times sine of 37 degrees. Okay, I believe this problem says it wants us to find, it doesn't say here, but let's go ahead and make this easy on ourselves. Let's round this out to the nearest mile. If I put this into the calculator, then I quickly find that r is approximately 2,383 miles. So apparently, if we travel up to the 53rd parallel of latitude, its radius, the distance from the center line at C out to the point here on the surface of the Earth, is 2,383 miles approximately. This leaves us with precisely one more problem to do, and it looks like we're going to have to do it on the next page. So, suppose from the top of the Empire State Building, which is about 1,250 feet high, we get an angle of depression to the top of some other building, and that angle of depression is 55.8 degrees. And then we get an angle of depression to the bottom of the same second building and find that it's 67.7 degrees. We want to find the height of the second building. Well, at first glance that sounds very challenging, but it's not as bad as it sounds. Let's go ahead and draw the Empire State Building. For those of you who know New York fairly well, Forgive me, I'm about to profane against all of New York. I have no idea how to draw the Empire State Building. I'm just going to take a stab at it. That doesn't look too bad, I hope. We know that this has a height of 1,250 feet. We also have some other building, which I'm going to put, I don't know, let's say right over here like this. It's going to be just some drab little rectangle. And what we are told is some information about angles of depression. So let's go ahead and first fix our point of perspective here, which is going to be at the top of the Empire State Building. We're going to make our line parallel to the ground, so in other words, our horizontal line. And we are now making angles of depression. I know in our picture on the previous page, we used red for angles of elevation and blue for depression, but I'm going to go ahead and use red and blue here for two different angles of depression just to make it a little bit easier to look at. So, apparently, if we measure the angle of depression to the top of the second building, like so, maybe closer to the edge like this, we're getting an angle of 55.8 degrees. But if we measure the angle of depression now to the bottom of the building, we get a different angle. Specifically, the angle that we get, it's a little bit messy here. I guess I'm going to have to be careful about this. The angle that we get the second time around is 67.7 degrees. And I want to make something clear in this picture. My picture is a little bit cramped. However, when I say 55.8 degrees, I mean from the black dashed line to the red line. When I say 67.7 degrees, I mean from the black dashed line to the blue line, all the way. I want to know the height of this building here. So in other words, I want to know what I'm going to call H, just to keep things simple in my diagram. Well, like I said, it sounds kind of tricky, and at first glance it looks tricky as well. But let me add in a line. I'm going to add it in green. If I add in another dashed line in green here, I'm going to make a right triangle. Actually, two right triangles. The first one is the one that goes through the black dashed line, the green dashed line, and the red dashed line. The other one is black dashed line, green dashed line in building, and blue dashed line. So we actually now have two right triangles here. And why am I doing that? Well, I'm doing that specifically because as I look at this picture, I'm noticing that if I added H and the height of this green line, which, I don't know, why don't we go ahead and call this E? E for error. It'll be like the error in our height here. If we added the amounts H and E together, we would wind up getting exactly the 1,250 feet. So I think this is key. I think if I can use this information to say, hey, E plus H is equal to 1,250, I can then use the angles I was given to get some other value. So the question is, what value could I get that would be important here? Well, I don't know. If I figure out, if I have the length of this side, H plus E is equal to 1,250, that tells me I have the total height of this second triangle, the one that has a 67.7 degree angle on it. I suppose I could use that to get the length of the blue line, but the length of the blue line doesn't seem to be linked automatically to the height of the building, at least not in an easy way. Oh, wait a second. I could get this length here from the point of perspective at the top of the Empire State Building to right above my building. I don't know exactly what I want to call that. I think maybe D makes sense in this picture. It's basically the distance from the top of this building to the top of my second building. D is interesting because D is part of both triangles. It's part of the one with the blue hypotenuse and it's part of the one with the red hypotenuse. So that might actually be really useful to me. Okay, if I had D, what could I do with D? Well, trying to shake off all sophomoric humor in this situation, it looks to me like if I knew what this length D was, I could probably use it and the angle 55.8 degrees to find out what the length E was. Ah, and there it is. Since I know that E plus H is equal to 1250, if I can find E, then I could subtract it away from 1250 and that will give me H. So, let's go ahead and make this a little bit cleaner and easier to follow, this thought process, with a plan of attack. I'm just going to go and write it out quickly. Okay, here is the three-step plan. First, we're going to use the bigger triangle to figure out what D is. If we can figure out what D is, we can use D and the smaller triangle to figure out what E is. Finally, since I know that when I add E and H together, I get 1250, which is how I know the height, the vertical side length of this bigger triangle, is equal to 1250, then I can simply use this equation and the value of E to figure out what H is. It seems like a lot of work, but it's actually not if we break it down into these small steps. So let's go ahead and start on the first of the small steps. I'm working with a triangle that has this 67.7 degree angle here. The side opposite that angle is 1250, and I want to figure out what D is. Since I want to relate this angle, this side length, and this side length here, it seems to me like I could use either tangent, which would do opposite over adjacent, or maybe more usefully, I could use cotangent, which would use adjacent over opposite. In other words, to do step one, I observe that cotangent of 67.7 degrees is equal to D, the length I want to know, divided by this whole side length, which is 1250. If I solve that for D, I'm going to find that D should be equal to 1250 times the cotangent of 67.7 degrees. You'll notice I'm not calculating D or approximating D at this step. I'm simply writing down what D is equal to right now. That should be all I need to do for step one. Step two. Now that I know what D is, I can figure out what E is. I'm working in the smaller triangle, the one that has 55.8 degrees at this corner. E is the side opposite, D is the side close by, the adjacent side. Since I want to figure out what E is, and I want to relate the angle in these two sides together, this time I think it makes sense to use tangent. Tangent says that if I take tangent of this angle here, I should get opposite over adjacent. So I write tangent of 55.8 degrees is equal to E, the value I don't know, divided by D, the value I just figured out. Once again, I can rewrite this. I want D to go onto the other side. The things I can calculate should be all on the other side, opposite from E, so I multiply both sides by whatever D is, and I find that E must be equal to D times tangent of 55.8 degrees. That should be all I need to do for step two. Finally, step three. Now I could write down the original equation I put here, that E plus H is equal to 1250, but I think everybody knows what I'm going to say. H is what I get when I take 1250 and I subtract E from it. Now, just to be clear, because we have gone through a couple of steps, what does that mean? Well, if we go back to the previous step, that means 1250 minus d times tangent of 55.8 degrees. When we calculated d, we found that d was equal to, and I'll put this in parentheses, 1250 times cotangent of 67.7 degrees. Finally, and this is the last thing I'll do before I actually calculate, and let me see, does it give us instructions for what it wants? It just says find the height. So once again, let's make this easy. Let's go to the nearest full foot. To make this easy on you, when I put this into the calculator, this is what I'm actually going to write. Instead of 1250 times cotangent, it'll be 1250 divided by tangent of 67.7 degrees. If I write it like this in my calculator, it should give me the correct answer, which I can then simplify. So let's go ahead and, not simplify, approximate. If I feed this all in, it looks like I'm going to get approximately 496. And if I go back up here, I remember that this was being measured in feet, so that would be approximately 496 feet, which is exactly the right answer. Whew. Again, it looks like a lot, but if you take it into steps, if you break it down into finding the pieces that you need, none of it is too bad. All right, for most of us, that should be everything, but USF folks still need a Canvas quiz question. So let me go ahead and put that down below. All right, the wait is over. The question is as follows. You have a plane. It's flying at a height of 3,000 feet above the ground, and it passes over, vertically, a helicopter. When it does that, in that exact instant where one is over the other, the angles to the two from the same point on the ground are 60 degrees and 48 degrees, respectively. Your job is to find the height of the helicopter to the nearest foot. I have a habit of giving out verbal hints here, so let me give a few. So, first things first, an obvious one, draw the picture. You're going to have a very tough time of this if you don't draw a picture. Draw the picture, label it carefully. Second thing I'll go ahead and say, this problem is relatively similar. It's not exactly the same, but it has some similar elements and ideas to what we did in the previous problem. So, if you can work your way back through the previous problem and our logic there, you will probably find that you're better situated to solve this one. And finally, think about, from the diagram and from the description of the problem, where the plane and the helicopter are. If you do that, you can probably weed out one or more possible answers here as being incorrect. All right, folks, that's all the time we have for today. Thank you so much for watching this video. I hope you learned something today. If you have questions, leave them in the comments or send me an email. And, as always, until next time, happy math.